So having studied the boundary layer theory, it is clear that high Reynolds number flows are prevalent in many applications of engineering. In particular, if we look at any kind of aerospace or transportation application, typically we end up with Reynolds number which is quite high. Atmospheric fluid dynamics, oceanographic fluid dynamics, municipal water supply, power generation, aircraft, ships, all these, I mean, whatever the phenomenon is sort of characterized by the Reynolds number rather high. And the consequence of Reynolds number being high, we have seen, is the presence of a thin viscous layer, but everything outside is sort of irrotational if the incipient flow is irrotational. So consider another application where you might have seen high Reynolds number flow. Well, you might not have seen, but you have definitely experienced is flow in your engine. So inside an engine inlet or exhaust, the suction of the piston. So the suction of the piston. So when this piston goes down, the inlet valve opens. So the opening of the inlet valve and the suction over here leads to a rapid drawing of air and fuel mixture. And that high Reynolds number flow is also characterized by a rapid mixing, because air and fuel have to be nicely mixed before entering into this chamber. If they are not completely mixed, you will have incomplete combustion. But at the same time, a violent mixing of air and fuel is also accompanied by the creation of lot of noise. Okay. Similarly, the gases coming out from a chimney, you can see that very quickly it starts to disperse. Okay. Such things all fall under high Reynolds number effects. They are not entirely diffusive in nature, and we will see some of the characteristics later on. It is actually quite difficult to define what the problem of turbulence is. Turbulence in general involves fluctuations. It involves fluctuations and the fate of the variables in the system, they are quite indeterminate. And consequently, many of the advancements in the area of turbulence have happened through physical insight, like scaling arguments. They have happened through statistical means, and in modern times they have taken place due to very high result CFD simulations. So very highly resolved CFD simulations. But at the end of the day, these things are nevertheless uh, still going to conserve. Okay, they are still going, the whatever the equation which governs transport of turbulent flows, it's still going to conserve mass, it's still going to conserve momentum. I mean, just because the flow behavior is something which is rather erratic, it doesn't imply that these quantities will not be conserved. And it is in these conservations, okay, that some of the physical insights can be had based on the dimensional analysis, based on estimates of energy, things like that. Okay. So there are some properties of turbulent flows I mean, which we will see in all kinds of turbulent flows. So the first property we have already discussed is fluctuations. Okay, so fluctuations means if you are sitting at a point with a probe and you are trying to plot a property theta as a function of time, so you will have a signal like this. It means that there is some broad mean, okay, there is some mean, but there is a fluctuation on top of that mean. As opposed to laminar flows you will always have smooth continuous solution. In turbulence flows, the effect of non-linearities is quite prominent, and the non-linearities are pathological to high Reynolds number only, because the Reynolds number being high implies that the inertia or the inertial contribution is rather high. It means that in the inertial terms you will have terms like rho u dot nabla u. So these kind of terms will give rise to fluctuations which are quadratic. So even though there is a fluctuation which is negative, okay, when you see the contribution of that fluctuation, it will be quadratic and u square. This kind of terms we will find throughout our analysis, and truly understanding how the energy is being transported from various structures in a turbulent flow is what gives us the key towards a deeper insight. Many of the problems in turbulence are still unsolved despite being formulated almost 120 years back. So turbulence is also characterized by vorticity. So if you look at various cross sections in a turbulent flow, and you can look at this on a nice cold day when you light a fire in a ground, okay, the smoke starts to come up, okay, and suppose there is a slit of sunlight coming in. There's a slit of sunlight coming in. It can be between the branches of two trees also. This kind of effect happens in my garden. So you can, when the sunlight hits perpendicular to this smoke, you will be able to discern various vertical structures, and you can see this when you are lighting agarbattis as well, or something else, but agarbattis. So you can see the presence of various eddies. So these kind of vertical structures are called as eddies, and typically they are of a variety of sizes. So the diameter or the size of an eddy follows a certain distribution, and the distribution of the sizes depends on the Reynolds number. So these eddies, they deform, they spin, okay, they coalesce, okay, they do many things. They can divide also. A lot of things happen, and this hierarchy of eddies is common to turbulent flows, okay, and these eddies are said to transfer what is called as the turbulent kinetic energy from one scale to another. So vorticity and in particular eddies play a very important role. Rather, I mean, eddies are there, but analyzing eddies helps us to understand the transfer of energy from various length scales to another. Dissipation. Like in the case of boundary layer theory, regardless of the analysis in the outer layers, so the outer layers behave like inviscid flows. So this is the viscous boundary layer. So at a very small region, viscosity is important. Similarly, there can be various length scale in the problem. There can be various length scale in the turbulent problem. So if this is the wall, okay, if this is some u infinity, this is the signal of u infinity. And if there is a large eddy which exists, okay, at a certain length scale L, then this eddy, if it were to become very small, okay, as L reduces, that is, if we have a spectrum of eddies, then the velocity gradient will be distributed over such a small distance that the velocity gradient is the most important dissipative mechanism. So the dissipation is given by tau ij Sij. It is proportional to this. This is a dyadic product, tau ij Sij. Not dyadic product, it's a double dot product. So Einstein summation convention, if we invoke it, it will be tau 11 S11 plus tau 12 S12 plus tau 13 S13 plus tau 21 S21 and so on. Okay, so this is the term which appears in the energy equation and is responsible for viscous dissipation. So various mathematicians and scientists have hypothesized that at the smallest scale, whatever energy is being transported to the smallest scale through the eddy has to be dissipated by means of viscous dissipation. So turbulent flows are signified by the presence of a large amount of viscous dissipation, and the presence of viscous dissipation implies that in order to sustain a flow, you must somehow keep on supplying energy. And how much energy do you need to supply? You must supply enough energy to overcome the viscous dissipation, which is sucking out energy from the problem. So viscous dissipation is also related to rate of entropy generation. So all these things are quite related, and you'd be surprised how much intertwined thermodynamics, fluid mechanics, nonlinear processes, non-equilibrium processes, everything is. Okay, it's quite beautiful. And the last thing that is characterized, rather that is a characteristic of turbulent flow, is dispersion. So if you take a cup of water and if you let things diffuse, okay, things will diffuse over a distance of L over a time L square by D, where D is the diffusion coefficient. So the diffusion coefficient is typically 10 to the power 9 meter square per second. So suppose L is 1 mm. So the time taken for the species for a particle to diffuse over a distance 1 mm will be 10 to the power minus 6 upon 10 to the power minus 9, which is 10 to the power 3 seconds. So 1 hour is 3600 seconds. So go do the math. So just to diffuse over 1 mm, it would take a huge amount of time. Okay, so in turbulent flows, it is seen that particles, they could diffuse extremely quickly, and the mechanism behind their extremely quick diffusion, or rather velocity aided diffusion, is called as dispersion, is the presence of large velocity gradients and fluctuations in the flow. So the presence of high Reynolds number is also tantamount to the presence of high Peclet number. So this kind of things, it will be clear when you study heat and mass transfer. And presence of high Peclet number means that you typically have a very poor diffusion, but because you are advecting the particle all over the place because of turbulence, you eventually end up particles being very close to each other on account of advection, and they need to only diffuse a very small distance. It's very much like if you pour a blob of cream in your coffee and then you start to mix the coffee. So when you give a whirl like this, so this blob will become something like this. So now for this blob to merge together, it has to only diffuse over this distance, and this distance could become very small. So it very quickly homogenizes. So the effect of turbulence is to very quickly homogenize things. Turbulent flows are poor in segregating or keeping things segregated. Okay. So these are what the basic observations are for turbulent flows. Typically, turbulent flows are three-dimensional. Turbulent flows are seldom two-dimensional, but in our atmosphere, the temperature stratification leads to a density stratification, and there is a layer of our atmosphere which is sort of uh, confined to move in a single layer. So these kind of flows are called as geostrophic flows. Geostrophic flows. So geostrophic turbulence is the analysis of turbulence in two-dimensional flows. And these do have a lot of applications. Using such kinds of theories, one can discern what is going on the surface of Jupiter, for example. Okay, and somewhat analogous to whatever is going on Jupiter is the dynamics of things that are happening on a soap bubble. Okay, if you ever look at soap bubble at a right at a very appropriate angle, you will see all sorts of vortices, eddies, things happening on the surface of a bubble. They're quite beautiful to look at, but they're notoriously difficult to photograph. Okay, you need to have a nice black background, you need to have a nice lighting, and so on. But with the help of an eye, you can able to see it, but with the help of a camera, it's difficult to capture. But so if you see that, so those theories do have relevance to whatever is happening at geographical scales. So by applying principles of similarity, you can sort of upscale the phenomenon happening on the surface of a bubble to that happening on planets. So whatever we have discussed is by no means a very complete discussion of turbulence, or rather the properties of turbulence. There are several books. If you're interested, you can look into Monin and Yaglom. They have a two series book. There is a book by a very famous book by Tenekes and Lumley. There's a very famous book by S.B. Pope. So each has their own way of tackling turbulence. There is no universally acclaimed method of tackling turbulence. Okay, and it is by no means something which has a very well struck path. It is a problem which requires very out of the box thinking. So the original ideas of turbulence were laid down by Reynolds in the year 1883. So his famous experiment involved a mouthpiece and a pipe, and there is a small syringe to inject some dye, and so there is flow coming in like this. So I mean, back in the day it was not called Reynolds number. He saw that when the flow rate was exceeding a certain rate, whatever dye you are injecting, if it is laminar, then the dye will keep on going like this. But when the flow rate exceeds a certain flow rate, this dye will become irregular. Okay, there is intermittency. So if you snap a photograph of the dye, there will be some intermittency, and beyond a certain flow rate, it will be completely turbulent. So the dye profile, it changes shape based on the flow rate. So after some years, Sommerfeld and Sommerfeld was a very influential scientist in the early 1900s. He had several contributions to classical mechanics, quantum mechanics. Actually, he was a very influential person. He had trained several PhD students, many of them who became top scientists, including Heisenberg. Thanks for ruining the recording, whoever you are. Yeah, so Sommerfeld later classified what he called as a Reynolds number. So Reynolds number does not have any apostrophe or something. The name of the person was Reynolds, Osborne Reynolds. Okay, so he defined what is called as Reynolds number and showed transition from laminar to turbulence. Okay, and Reynolds number was critical in understanding the process of transition from laminar flow to turbulent flow. Then the problem was attacked by G.I. Taylor, who described dispersion, and G.I. Taylor laid the groundwork for a lot of processes which involve high Reynolds number, high Peclet number, and it goes around by the name of Taylor dispersion. So Taylor dispersion is something which you will find in laminar flows as well. It is there in turbulent flows. He also laid down the formulation for dispersion in terms of a random walk. And diffusion in terms of a random walk was something which was laid down by Einstein. So as you can imagine, I mean, things in this field have progressed significantly because of contributions from excellent minds, from people who have really thought outside the box. Then the school of Prandtl, von Karman, Wohlhausen. Okay, this is what is known as the Göttingen school of fluid mechanics. So the Göttingen school of fluid mechanics, they had several contributions which involved the Prandtl mixing length theory. Then, I mean, it was later disproven, but it did show us an empirical way of approaching. I mean, whatever it is, theory is something which helps us in either disproving or proving or making some progress from that point onwards. So never be afraid to propose your theory. If it's disproven, then at least you know that it doesn't work. There is no doubt. So a very critical contribution also came from Richardson, and the work of Richardson laid down the formulations for spectra, turbulent spectra, and he actually did a lot of measurements from weather balloons and was able to show a bunch of things. Based on the work of Richardson, the extremely famous and one of the brightest mathematicians of this earlier century, Kolmogorov and Obukhov. So as you can imagine, Soviets. So they did very fundamental works on approaching turbulence from the viewpoint of statistics and stochastic processes. Okay, in fact, the book of Pope and Monin and Yaglom in particular, they deal with such kinds of stochastic processes. So we will also take the statistical route. So the way we will move forward is we will first discuss some of the nomenclature that exists in turbulent flow. We will discuss the Reynolds decomposition. We will look at the log at the velocity profile near a wall. Okay, we will not. Okay, this is what we plan to do, and through this, while it is, I don't expect you to wholly appreciate whatever is going on. What you should appreciate is things are not as straightforward as saying that okay, things are very random, chaotic. No, I mean, things are not random, things are not chaotic. Random has a very specific connotation mathematically. Chaotic has a very special definition mathematically. What you may feel as random, what you may speak with your friends as अरे random चीज हो गया. So things like that, they have no place in analyzing such kinds of processes, and things have to be very precise. Okay. So let us proceed and discuss about some of the nomenclatures.